Hi, everyone. It's a pleasure to be here. Thank you so much for the opportunity to share a little of the work that I do as a genetic counselor, both on the clinical side and the clinical research side in our pediatric hearing loss clinic at Boston Children's Hospital. I put my fun lab slide right up front. So this is the translational hearing loss genomics laboratory at Boston Children's Hospital. So I work with two otolaryngologists, Dr. Elliot Shearer and Dr. Margaret Canay, who've been practicing as ENTs for a long time and have a really special interest in the genetics of hearing loss, which I do as well. We are a translational lab, so I see patients on the clinical side, kids with diagnosis of sensorineural hearing loss. And my main goal in the part of this flowchart is really to find the diagnoses for our patients. Hearing loss may be the symptom for the kids that come in, but what's the underlying cause or explanation for their hearing loss or deafness? And then, continuing in our flowchart, we have people working on the basic side of things, trying to elucidate, a molecular mechanism for interesting genetic variations, novel candidate genes for hearing loss, animal models. We're moving towards more of an inner ear organoid model to model our patients' specific, rare form of hearing loss, and ultimately with the goal of developing targeted gene therapies for specifically our patients' individual.
Sorry to interrupt, but I feel
can't
like you
hear?
took your mic off by accident.
Oh, if I'm going to be talking about hearing loss, I better have the mic on. Thank you. Is that better? Okay. So I'm going to be focusing a lot just on hearing loss, the genetics of hearing loss. I really care a lot about the clinical side of things, so I wanted to share a little bit about what my life looks like as a clinical genetic counselor. So 1 in every 500 newborns will be diagnosed with a sensorineural hearing loss, and an early diagnosis for these kids is really so important to foster communication development, spoken language skills. There's a really critical window where if you're not knowing that a child is deaf or has a hearing loss, they kind of miss those crucial years. So the early diagnosis is really important. One of the most successful public health initiatives kind of overall in the US has been the newborn screen, which is a screen that any of you have had kids probably remember. They take few drops of blood from a baby's heel within 24 to 48 hours of birth, and they also do a little hearing test for the new babies. So if we look at all the different diagnoses that are screened for on the newborn screen, which has been around for quite a while, and they've been adding more and more conditions. Hearing was started screening for hearing in the mid-90s. These are the number of kind of positive results from the newborn hearing screen. This is on the y-axis we have out of every 10,000 births. You see these are the numbers of kiddos who will test positive for all of these other conditions screened. The most common I'm showing right now is for congenital hypothyroidism at 6 out of every 10,000 newborns. But the hearing screen is 16 out of, so it's by far the most common diagnosed on the newborn screen. Any kids that are diagnosed or suspected of having this early hearing loss will be sent over to our clinic for a full workup, and they'll get hearing aids. They may need a cochlear implant, all of that sort of clinical care. So, talking about the importance of an early diagnosis from supporting speech and language, but early identification of a specific cause of their hearing loss can have a very important role to play as well. One thing that helping with a specific etiology gives us is prognostic information. Will the child have a progressive hearing loss? And about half of the most common genes that cause hearing loss will progress. Their hearing loss will progress over time. It helps aid in surgical planning decisions. The specific cause and other sort of non-extra auditory features or other aspects of the hearing loss may really change plan on whether a child will get a cochlear implant or hearing aids or be an ASL user. Most importantly, from my perspective as still not working? Thank you. Okay, thank you. How's that? Oh, good. Well, hopefully you're more or less still with me at this point. One of the things that's most important to me as a clinician on the genetic side of things is evaluating for a syndromic form of hearing loss. Hearing loss or deafness is often the earliest presenting symptom of a genetic condition, and many more things can follow from there as a part of these more complex syndromes. So finding that early diagnosis can have really important consequences for the individual patient. It can also have really important consequences for families on the understanding recurrence for these conditions on the family planning side of things. And I also find, that the deaf and hard of hearing community is a really strong community with a distinct culture. And empowering families to understand more about their child's diagnosis and understanding a little bit more about specifically where they may fit in within this community and culture really fosters a sense of empowerment for parents and, in my experience as a clinician, and ultimately for these children as they grow into adults. Genetic testing is the most powerful tool that we have to understand hearing loss. 40% of hearing loss, depending on the paper that you read, and this number fluctuates, but I think 40% is a really great estimate of the number of genetic tests that you send out that will come back positive for kids with hearing loss. There's also structural abnormalities of the inner ear, so cochlear abnormalities that contribute to hearing loss. And other tests that you can do, like scanning the kidneys or the heart, help to understand any sort of extra auditory features that might give you a sense of what's going on with your patient. But ultimately, genetic testing is really the most powerful tool to understanding for these kids. We've covered some of this already. 1 in 500 kids will have a congenital hearing loss. 50 to 70% is estimated or suspected to have a monogenic etiology. We're not always finding those numbers when we actually do the testing, which is kind of the reason we're all sort of here today, is try to get better at actually finding those positive diagnoses. 30% will be syndromic, whereas 70% will be non-syndromic, just a genetic cause that's isolated to the hearing loss. I've highlighted some of the most common syndromic causes of hearing loss here, Usher syndrome being a really important one in terms of, community and planning. So Usher syndrome is usually a child's born deaf at birth, but will sort of quickly lose their vision over time and ultimately be blind. And so, really that diagnosis carries a really powerful weight for our patients. And on the non-syndromic side, most is recessive, 80% is recessive, some dominant, and mitochondrial, and some other forms, X-linked as well. And we have a very long list of candidate and known hearing loss genes, so I had to update this slide before coming because the list just keeps growing. The first hearing loss gene to be described was in 1997, so relatively recently, and the list has just shot up since then. But discovery is sort of slowing down. We've found a lot of the easy ones to find already. But that's another interest of our lab that I won't speak on today, is novel gene discovery for hearing loss. Diagnostic rate definitely varies by clinical characteristics. So we have this overall 40% diagnostic rate, but if we have a really strong family history, generation to generation, we find that we have a 50% chance of having a positive genetic result by our sort of conventional clinical testing methods right now, which is a large gene panel for the most part. Age of onset is a really good indicator of how likely we are to find a hearing loss, where a congenital hearing loss is easier to find an explanation for than an adult onset hearing loss. And then bilateral hearing loss is same story, much more likely to have a positive genetic test than a unilateral hearing loss, but we see that this number is shifting as well. The more genetic testing we do for kiddos that don't fit perfectly into the box of, bilateral severe to profound hearing loss, we're really expanding what we know about the phenotypic spectrum of some of the genes that we're testing for. So even though we've come a long way in understanding all of this, and I think a 40% overall diagnostic rate, when you think of all the different rare disease indications, is really good, but we know that there's a lot of room to improve. We see so many cases day to day where we have a really high suspicion going into a clinical evaluation that we will find a result, and then we just don't. And so that's where some of the research that I'm going to talk about in just a minute, where it comes in. I've heard a lot about today already, all these different types of variants that you just can't do a good job of finding with short read sequencing. And I like this slide just to show, we've picked a lot of these low-hanging fruit, and I know that most of you have probably done the same in your work as well. So our goal is really to work our way up the tree. We need a taller ladder, both on understanding our genotypes better, and then finding the actual underlying genetic cause of some of these phenotypes that we don't understand as well. I mentioned unilateral asymmetric hearing loss, and just more genetic discovery. So this is our clinical workflow for the work that we do at Boston Children's Hospital. I provide genetic counseling to all of our research participants and walk them through exactly what these tests are and why we do them. Many of our patients will be able to access a clinical gene panel through insurance, and we find about 30% overall diagnostic yield for our patients that can access that testing. But many patients cannot access that testing still for financial reasons, and so we're very lucky to be able to offer genomic sequencing through our research studies to anyone who has either a non-diagnostic test through our clinic or cannot access the testing through their insurance. So we consent them to our research study. We have a very robust cohort of kids that have had trio exome sequencing. And then right now, not for all of our families, but for many, we're able to reflex to a short read genome sequencing panel. Similar to what our first speaker was describing, we're also very lucky to have a built-in clinical confirmation process for the variants that we identify. So all of our research results can be sort of effectively turned into a clinical result that can be in our patient's medical record and make a real difference in their care at no extra cost. And then that's when my genetic counseling hat comes back in. I return the results to the families with genetic counseling at the end of this process. So this is where we're at with our exome so far. So we do a pretty good job. These are for the kids. It's kids that have had both a panel before, have never had genetic testing before. Our overall result with exome sequencing, our yield is just under 30% at the moment. Our yield may be a little bit lower than what you will read in published studies, because we're really inclusive of any phenotype. So the most mild hearing loss, unilateral hearing loss, we want to test everyone and see what we can find. But we see so many non-diagnostic cases that are really frustrating. We see this huge diversity of genes. GJB2 is sort of our main culprit, as well as STRC, stereocylin, which we'll hear about in a little bit some more. And then we see many, many different super rare genes, many of which, we're lucky that we can do exome because they would have been missed on a conventional gene panel, but it just makes us think, what else are we missing? Of our 280 non-diagnostic patients so far, we've been able to reflex just 90 of those to short-read genome sequencing, and have only found one additional diagnosis. So I think that can show you where we're still really lacking when you're already increasing the test size so hugely, but not really able to find more results for our patients with our short-read genome sequencing. So this is where our, there we go. This is where we know that our missing diagnoses are probably lie. I think A huge part of it is variants in genes that have just not been associated with hearing loss before. That's a real challenge. But then we know there are a lot of areas of real complexity, segmental duplications, pseudogenes in hearing, like in the regions of our hearing loss genes that we see all the time. We're missing out on a lot, and we know that, and you all know that as well. So I wanted to share one patient story just to demonstrate what these diagnostic odysseys kind of look like for our families. This is Emily. We've been following her since she was born. This is her audiogram. So normal hearing should be all in like the white or gray area. So this is her audiogram, and it's in the sort of moderate to severe range. She's done pretty well with hearing aids, but her hearing has progressed pretty significantly over time, and she's really sort of struggling to hear in school at this point. So she's 11 now. Everything under the sun has been ruled out, so she had lots of tests for congenital infections at birth, normal imaging of the ear, normal physical exam. Her development has been totally typical, and she had a whole panel, a whole slew of genetic tests, starting with a single gene all the way up to short-read genome sequencing. This is over the course of the 11 years that we've been trying to figure out what was causing her hearing loss, and it's all been non-diagnostic. This is where our partnership with PacBio came in. So we were lucky enough to be able to just sequence a pilot sort of cohort through our umbrella research organization at Boston Children's Hospital of 19 probands that had a sort of high prior suspicion of a genetic hearing loss that had gone undiagnosed. And of the 19 families that got long-read sequencing with you guys, we were able to find a diagnosis, or what we feel is a diagnosis, for 4 of those 19. So these were families that had a congenital bilateral hearing loss. Some of them had a pretty strong family history of hearing loss before, or they had extra auditory features that were suspicious for a particular syndrome that we just weren't able to diagnose. I can break down some of those diagnoses now. We actually heard our first speaker mention this gene as well, STRC. It's a super common cause of a mild to moderate hearing loss. And so of the 4 diagnoses that we made using long-read sequencing, 2 were actually in this gene, 2 unrelated kids with a mild to moderate congenital hearing loss. Their clinical panel had identified that they had a heterozygous deletion in this gene, which is really common. But because of the presence of a pseudogene that has over 99% homology with STRC, it's really difficult to resolve, actually sequence this gene and have good variant calling. So when we first ran these samples by all of our methods, these single nucleotide variants in the STRC gene were not called. They were just totally missed. So we knew that they had the heterozygous deletion. Long-read sequencing was able to confirm that and also identify pathogenic single nucleotide variants in this gene. And this was a really meaningful result of both of these families, because actually both families individually went on to have a second baby that was also diagnosed with hearing loss. And I think it gave the families a lot of comfort to know why their child had the hearing loss, and also that it was a non-syndromic hearing loss and that they didn't have other health issues to sort of be planning for or worrying about. Similar story for our third diagnosis is in the otoancorin gene. This is a gene that is known to cause a non-syndromic progressive hearing loss with those sort of U-shaped audiograms like I was showing before for our example patient, Emily. Again, long-read sequencing was able to identify both a small deletion and a pathogenic single nucleotide variant in trans, both of which had been completely missed by other sequencing methods, because this isn't a really complex segmental duplication, high GC content, just a really difficult area to resolve. And then lastly, we found an interesting inversion in this MITF gene, which causes Waardenburg syndrome. So Waardenburg syndrome is a hearing loss as well as pigmentation abnormalities of so differences in the skin, hair, eyes, in their coloring. And this patient had an inversion, kind of copy number neutral inversion that is suspected to affect some of the alternatively spliced transcripts of the MITF, and so we were sort of hypothesizing this might be why she has a kind of less obvious clinical presentation of this syndrome, and it really helps us understand like the phenotype a little bit better. So these results, I had the honor of working with these families for several years to get to these results, and we were able to get like a clinical confirmation for all of these variants that we felt were diagnostic from sort of our orthogonal methods to our research long-read sequencing. I had the pleasure of returning these results to the families, and the mother of the patient, Emily, who I described, was so happy that she started crying in my office, and so she's just been searching actively for 11 years. And she's reported having a real sense of peace and gratitude now that she has this explanation. So I think I'm here just to sort of promote the real life consequences that these types of diagnoses have for our families, and the real power that this new technology that we've been very grateful to be able to make use of. We found 20% of the cases we've pushed through have found new diagnoses so far. So with that, thank you very much. Thanks to my lab, and thanks to PacBio for having me here today.